Hi again, it's Mr. Fig. For the last video, the last lecture video of the week is exploring the equations that govern these spherical mirrors. Now again, so far we've been looking at ray diagram and using simple geometry to figure out where the images will be, and that works great. But the difficulty is I need to make sure my drawings are drawn to scale. I need to make sure that the spherical mirrors are drawn as true circles. I need to measure where the center is. I need to measure where the focal point is. And all that can be a little bit cumbersome, especially if I'm dealing with a situation in the real world and I just want a quick answer. So there should be a way to determine this information using algebra and equations, and there is. So we're going to look at the equations governing these mirrors. Now, these are an important set of equations because although you might not come across that many spherical mirrors in your day-to-day life, although you do have them, we talked before about how if you use a makeup mirror or a shaving mirror, that's an example of a spherical mirror. And the side mirror on your car that shows a wide angle view, that's also a spherical mirror. But these same equations will be useful when we talk about lenses. And as you can see, for me, unlike a lot of people, I have lenses on right now. And these same rules and equations will be useful when we discuss how eyeglasses work and how our eyes work later on as well. So let's take a look at these mirror equations. And then the final video this week, I will do some practice problems out so you can watch the setups of these questions and get to the homework assignment this week. All right, let's go. All right, so as I mentioned, the ray diagrams are useful, and we looked over the last couple of videos of how to construct these ray diagrams, that I have an object, and I send incident light to the mirror. I follow my 3 rules to draw the reflections. But a ray diagram requires that I draw my rays very carefully. It's a little bit easier actually for me to do it on a computer than by hand, because I can use the computer to make sure that my lines are straight and my mirror is a circle and such. The drawing must be drawn to scale. That is, if I was trying to find the image of a particular candle in the real world, I would need to make sure that the height of this candle is drawn such that it's obeying the same scale as, say, the distance from the center to the mirror or from the focal point to the mirror. And if I wanted to find out how high this image really is, I would need to use a ruler and measure the height of that image. And again, I need to make sure that everything is very careful in my drawing. So a ray diagram is useful to understand why the light is doing what it's doing, but it's not so useful to make predictions in the real world. So there should be equations for this. And the good news is there is. So let's take a look and see how we can solve these problems algebraically. All right. There is a difficulty using the mirror equations, though. All right, so the equations that we're about to give will only work if we use a specific set of sign convention. That is, there are certain circumstances where you have to remember when one of the mirror variables are either positive or negative. If you don't get the signs right, the algebra will lead to the wrong answer. So as important as the 3 rules for the ray diagrams were, these sign conventions are just as important to know, and you should probably make note of them on a piece of paper and keep track of them, especially when you first start doing these problems. So what are the rules for these variables? All right, first, the object distance and the image distance, P and Q, or as some books and websites will call it, DO for the distance to the object, or DI to the distance to the image. When they're on the real side of the mirror, they need to be positive numbers. When they are on the virtual side of the mirror, they need to be a negative number. Now, for us, an object will always be real. If you just have a single mirror or a single lens, you can only have a real object. Some advanced courses, you'd look at systems of lenses, systems of mirrors, and then it's possible to have virtual objects. But in first year physics, generally, we don't cover that. Now, the focal length and center curvature obey the same rule. The focal length and center curvature are positive when they're on the real side of the mirror and negative when they're on the virtual side. So if you recall last week's video when we were looking at convex mirrors, a convex mirror would have a negative focal point. because the focal point was on the opposite side from the real object. A concave mirror has a positive focal point. And finally, we have to remember the rule for heights. If the object is upright, then we must make the height of that object positive. If the image is upright, we must make the height of that image positive. But if the image is inverted, if it's upside down, then that height must be negative. All right, these three rules are incredibly important because without these sign conventions, the math will lead to the wrong answer. All right, so what are the mirror equations? All right, without much fanfare, here are the mirror equations. There are two. First, there is an equation for the magnification of the image. The magnification is simply defined to be the height of the image over the height of the object. Now, we'll see in a minute where this equation comes from, but by simple geometry, the height of the image divided by the height of the object will also be equal to negative of the distance to the image over the distance to the object. So Q over P, or again, some books would call this DI over DO. But that negative sign is important. Remember we said that our objects are almost always positive, but our images can be upside down for a virtual image. If this height is, so that's why that negative sign needs to be there. So that negative sign is very important when using the magnification equation. And then there's the mirror equation itself. The mirror equation states that 1 over the focal point is equal to 1 over the distance to the object plus 1 over the distance to the image. And again, some books would say 1 over DO plus 1 over DI. I'm just using the traditional variables because it matches what's in our text. So these very two simple equations are all it takes to determine the reflections from a mirror. But they only work if you use the correct signs, especially in the mirror equation. Knowing when to put in a negative value for the focal point or the image distance is incredibly important, or else this math won't result to the right answers. So the question is, where do these equations come from? Well, let's take a look at that. So first off, normally in a normal year where we're teaching in the classroom, time is short, and most of the time I don't take time to actually do the derivation of these equations. So if you're a trusting person by nature and you don't really need to know where these equations come from, and you just want to take our word out for them, that's okay. In fact, if that statement sounds good to you, then you can stop watching this video right now and just go on to the video where we do the practice problems. Okay? I don't expect you to understand the derivation of these equations. It's not too tough, but being able to use the equations is our primary goal. But if you're mathematically curious, hang on and I'll show you, we'll do the derivation together. So I'll wait for a minute. Those who would like to leave the room can go leave the room. Those who would like to see the math done, let's go take a look. All right, I have here a ray diagram for an object in front of a concave mirror. Now, it looks similar, but it's a little bit different. Now, let me point out the difference. I have an object here in front of the mirror. I do send a ray through the focal point, which reflects parallel. Now, that's one of our 3 rules that we've been following. You might notice that this ray is done a little bit differently. I'm sending a light ray from the top of the candle. And again, the light goes in all directions, so I can free to pick any light ray I want. And I'm striking it to exactly where the principal axis strikes the mirror. Well, remember that a principal axis line is also a normal line because this is perpendicular to where the light is hitting the mirror. So I know how this light reflects. So it may not be one of our 3 rules, but I can still make this reflection. The angle here above the normal line has to be equal to the angle below the normal line, so my reflections still cross right there, and that's where I would see the image. I would like to use this diagram to derive the mirror equations. Now, to derive the first equation, what I note is the object. If I look at the object and the light going to the mirror that strikes at that principal axis point, It is delimiting a triangle right here. Now I'm going to go do the same thing below the axis. The image also makes a triangle. So I have two triangles here defined with one side being the object for the green triangle and the image being a side of this red triangle. Well, I can use these two triangles to derive our first equation. So let's take a look at these two triangles separately. All right, the first thing I note is I know the angles here at the apex of the triangles. Because of the lower reflection, whatever this angle was striking the mirror had to be the angle of the reflected ray coming off. Now, I also know these two angles here because these formed right triangles. Now, I have 2 out of 3 angles identical in these triangles. That means the third angle in the triangles must also be identical because all 3 angles of a triangle must add up to 180 degrees. So if they have 2 identical angles, the third angle must be identical as well. I'm going to label that with phi simply because we already used theta and it doesn't really matter what we use because we're not going to do any trig with these angles. So I have 2 angles with 3 identical triangles. You may remember from geometry class, if 2 triangles have 3 identical angles, those triangles are similar. That means I can set up ratios comparing the sides of these triangles. So what are the sides of these triangles? Well, the green triangle was defined by the object, so the distance between the object and the mirror was simply distance p. For the red triangle, that was the image to the mirror, and that is defined by variable q. And for the sides of these triangles, well, they're simply the height of the object and the height of the image, where I put a negative sign there because the image was upside down, and that's one of our conventions that I need to follow. So based on this information, getting the first equation is actually very easy. Because these are similar triangles, I can set up a ratio. That is, I can say that this side of the red triangle divided by this side of the green triangle, or minus hi over ho, must be equal to this side of the red triangle divided by that side of the green triangle, which is q over p. And you can spot right away that that is simply the magnification equation. So the first equation is really easy to get. It's simply the fact that the way we drew our rays, we defined 2 similar triangles, and using that geometry, we get the equation. Kind of nifty use for geometry. For the mirror equation itself, we're going to have to do a little bit more work. But still the same kind of trick. Again, I'm starting with the exact same diagram before, but we're going to look at 2 different triangles. I'm still going to be using this object, but I'm going to look at the triangle designated by the ray that's going through the focal point. So I'm looking at this green triangle right here. And I want to compare it to the triangle defined on the opposite side here, where this is defined as, now this is a little bit tricky, this red triangle is a little bit tricky, but notice this side of the triangle is equal to the focal length, and this side of the triangle will still be equal to minus hi. So I'm going to work with these 2 triangles now to get the mirror equation out of it. So let's take a look at them more closely. So here are my green and red triangles again. I'm going to do the same thing I did before. Let's mark the angles to see if they are in fact similar. Because of alternate interior angles, these 2 angles here need to be identical. And so that's again from geometry. I have 2 right angles there. So again, these 2 right angles are identical. So the green and the red triangle once again has 2 of the 3 angles are identical. Since all 3 angles need to add up to 180 degrees, that means that the third angle must be the same as well. And I verified that these 2 triangles are in fact similar. So let me label the sides. Now the sides are a little bit tricky. Again, this green triangle side was defined by the height of the object, and the red triangle was defined, this side was minus the height image. Again, the negative sign because the image is upside down. But the other side of the triangles is not the same as it was before. For the green triangle, Well, this was not the full distance to the mirror. This was the distance to the mirror from the object, but minus this focal point. So this side of the triangle is P minus F, or again, some books would say DO minus F. For the red triangle, the way I drew the triangle, that side of the triangle is equal to the focal point. So these are the setups of my two triangles, but now I'm going to do the same trick with ratios of sides, and I'll have to do a little bit of algebra to get the equation to where I want it. So let's take a look. I start with the same idea as before, minus HI, this side of the red triangle, over HO, that side of the green triangle, must be equal to F over P minus F. And so I'm setting up ratios of my two similar triangles. Well, I can rearrange this a little bit. Well, first, before I do that, I make note that I can use the magnification equation that we derived earlier, because I can replace this HI and HO with a minus Q over P. That means that minus HI over HO is simply equal to Q over P, and the equation becomes a little bit simpler. So now I have Q's, P's, and F's in my equation. So again, all I did was take that simple ratio and replace HI over HO using the magnification equation. All right, well, that doesn't look like it, but that is the mirror equation. I just need to work it to get it into the right form. So let's do some algebra. The first thing I note is I'm going to flip both of these fractions. So I flip the Q over P to make P over Q, but if I flip that side of the equation, I have to flip the other side as well. So I take F over P minus F, and I make that P minus F over F. So all I've done in this first step is flip this equation over. Then I note that I can split up this parentheses by taking P over F minus F over F. Well, that would be P over F minus 1. Okay. Well, what do I do next? Well, it's not clear why, but what I'm going to do is factor a P out of both sides. On the left side of this equation, if I factor out P, that's the same thing as P times 1 over Q. That is 1 over the distance of the image. On the right side of the equation, if I factor out the P, well, P times 1 over F gives me the P over F part. P times minus 1 over P gives me the minus 1. So this does match what I have written here. But I have P on both sides. If I have P on both sides, I can cancel it out. And then I'm simply going to do a little rearranging and bring this 1 over P over to the other side. And I get that 1 over F equals 1 over P plus 1 over Q, which thus is the mirror equation. So there you go, just with a simple application of, well, it was geometry, right triangle geometry, and with similar triangles, and it was algebra 1, we can get the mirror equation. Now, you don't need to know this derivation. I wouldn't expect you to produce this derivation, but it's kind of nice to know that we can understand where these equations come from. And if you do understand this, you can consider yourself a bit of a math wizard, because you're doing math magic there. So there you go. So a little bit of math gives us a very useful equation. All right, so the next thing to do is just go on to the next video where we practice using this equation with some examples, and then you should be ready to tackle this week's assignment. See you there.